What if you woke up tomorrow morning, looked out your window at the pre-dawn sky, and the moon was simply gone? Not dimmed, not hidden behind clouds, not in a different phase, just gone. A blank black space where humanity's oldest companion has hung in the sky for 4.5 billion years. No crater, no debris field, no explanation, just absence. A hole in the night that every human being on Earth would notice within hours, and whose consequences would begin unfolding within seconds. Not days, not weeks, seconds. Because the moon is not just a pretty light in the sky. The moon is a machine, a gravitational engine that has been running the systems of this planet since before the first cell divided in the first ocean. And the moment it vanishes, every one of those systems begins to fail. Let's go second by second, because that is how fast this begins. In the first second after the moon disappears, you wouldn't feel anything. You wouldn't know anything had changed. The light that was reflecting off the moon and traveling toward Earth would still be in transit. It takes about 1.3 seconds for light to travel from the moon to Earth. So for exactly 1.25 seconds, the moon's reflected light would still be arriving. The sky would still show the moon, or at least its ghost. And then, in that second heartbeat, the light stops coming. If it's nighttime where you are and the moon is up, it simply winks out. Instantly. One moment it's there, full or crescent or half, depending on the phase, and the next moment there is nothing. Just stars. Just dark. The psychological impact of this moment, if you witnessed it, would be shattering. Human beings have never, in the entire history of our species, seen the moon simply vanish. Every culture on Earth has stories about the moon. Every calendar system in human history has been organized around its cycles. Every tide, every lover's walk on the beach, every poem written about moonlight, all of that is rooted in the assumption that the moon is permanent, eternal, fixed. To see it simply disappear would trigger an immediate, visceral panic unlike anything in recorded human experience. Within minutes, every telescope on Earth would be pointed at that empty patch of sky. Within hours, every government on Earth would be in emergency session. Within days, the question of where the moon went would consume every broadcast, every conversation, every waking thought of every human being on the planet. But by then, the physical consequences would already be well underway, and they would be far more terrifying than the psychological ones. Within the first few minutes, the most immediate physical change would be happening in the world's oceans. The moon is the primary driver of Earth's tides. It pulls on the oceans with its gravity, creating the familiar rhythm of high tide and low tide that has shaped coastlines, ecosystems, and human civilizations for as long as any of them have existed. This gravitational pull is not instantaneous. Tidal forces propagate through the ocean at the speed of long waves, which is fast, but not instantaneous. But within minutes of the moon's disappearance, the tidal bulge that the moon was maintaining on the side of Earth facing it would begin to relax. The great swell of water that the moon had been holding slightly higher than average would start to slump back toward equilibrium. And this slumping would not be gentle. The oceans have momentum. Water has inertia. The tidal bulge that the moon maintained wasn't just a static hill of water. It was a dynamic, constantly moving wave propagating around the planet as Earth rotated. Remove the force driving it, and that wave doesn't just stop. It oscillates. It sloshes. In the first hours after the moon disappears, coastlines that were experiencing normal tides would suddenly find the tidal pattern going haywire. The regular rhythm of tide, the predictable 6-hour cycles that fishermen and sailors have relied on for millennia, would dissolve into a chaotic, irregular oscillation. Not a catastrophic tsunami, not immediately, but a deeply unsettling, unpredictable churning of coastal waters that would make navigation dangerous and strand boats that expected certain water depths. The sun also produces tides, often forgotten because the moon's tidal force is about 2.2 times stronger. Without the moon, we would still have solar tides, but they would be dramatically weaker. The difference in tidal height between high and low tide would drop by roughly 2/3. The great tidal ranges that shape places like the Bay of Fundy in Canada, where the tidal difference can reach 16 meters, or the Severn Estuary in England, would shrink to pale ghosts of themselves. And this matters enormously, not just for the drama of watching the tide come in, but for the ecosystems that have evolved over hundreds of millions of years around the specific tidal rhythms that the moon created. Intertidal zones, the strips of coastline between the high and low tide marks, are among the most biodiverse environments on Earth. Creatures like barnacles, mussels, sea anemones, crabs, sea stars, and countless species of algae and invertebrates have evolved their entire life cycles around the precise rhythm of the tides. Their feeding patterns, their reproduction, their oxygen intake, all of it is calibrated to the moon-driven tide. Remove the moon, and you remove the rhythm. The intertidal zone collapses. Species that can only reproduce during specific tidal conditions, and there are many, would fail to reproduce. Species that feed only when the tide exposes the rocks, and there are many, would starve. The cascade of ecological consequences in coastal environments alone, in the first weeks after the moon disappears, would be devastating. And that's before we get to the bigger problems. Because the tides are just the beginning. The moon does something far more profound for this planet. Something that operates on a timescale too long for any individual human to notice, but whose importance to the stability of life on Earth is almost impossible to overstate. The moon stabilizes the axial tilt of the Earth. Right now, Earth spins on an axis tilted at 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is what gives us seasons. It's why the northern hemisphere is warm in June and cold in December. It's why the midnight sun blazes over the Arctic in summer and polar night descends in winter. The tilt has varied slightly over geological time, between about 22.1 and 24.5 degrees, but it has stayed within this narrow range for hundreds of millions of years. And the reason it stays in this range is the moon. Without the moon, Earth's axial tilt would not be stabilized. Under the gravitational influence of the other planets, particularly Jupiter and Saturn, the giant planets whose gravity reaches across the solar system, Earth's axial tilt would wobble wildly over millions of years. Computer simulations suggest that without the moon, Earth's tilt could vary between nearly 0 degrees and as much as 85 degrees over timescales of tens of millions of years. Think about what that means. A tilt of 0 degrees means no seasons at all. The equator would be permanently broiling, the poles permanently frozen, the entire planet locked into a rigid, unmerciful temperature gradient. A tilt of 85 degrees means Earth would be essentially rolling on its side, the poles pointing almost directly at the sun for half the year and away from it for the other half. At 85 degrees, the poles would experience months of direct sunlight reaching temperatures that currently belong to the tropics, followed by months of absolute darkness and cold beyond anything currently experienced anywhere on Earth. Now, this wouldn't happen tomorrow. The axial tilt doesn't change on a timescale of hours or days. It changes on timescales of millions of years. So this consequence of the moon's disappearance would be imperceptible to any individual human alive today, or to the next 100 generations of humans. But it is perhaps the most devastating long-term consequence of all, because the stability of Earth's axial tilt is one of the foundational reasons why complex life evolved here at all. Mars, which has no large moon, has experienced chaotic axial tilt variations over geological time. Its tilt has ranged from near 0 to perhaps 60 degrees, and Mars is a dead world. Whether the axial chaos contributed to its lifelessness is debated, but the correlation is striking. Earth's moon has been our gyroscopic anchor, keeping our planet's orientation stable enough for complex ecosystems to evolve and persist over hundreds of millions of years. Lose the moon, and eventually, over geological time, lose that stability. But let's come back to the short term. Because in the hours and days and weeks after the moon disappears, there are more immediate crises unfolding. And some of them are ones that most people would never think of. Consider the length of Earth's day. Right now, a day on Earth is 24 hours long, but it wasn't always this short. When the moon formed, about 4.5 billion years ago, Earth was spinning much faster. A day was only about 6 hours long. The moon's tidal friction has been gradually slowing Earth's rotation over billions of years, stealing rotational energy from Earth and transferring it to the moon's orbit, causing the moon to slowly spiral outward. Without the moon, that braking force vanishes. Earth's rotation would no longer be slowing down. It would just continue at its current rate indefinitely. This sounds like a minor thing, but consider the implications over millions of years. Without tidal braking, our days would stay at 24 hours rather than slowly lengthening. This might sound fine, but it also means the dynamic we have with the moon, the energy exchange between Earth's spin and the moon's orbit, which has been a stabilizing force for the entire system, is gone. The day-length question is less dramatic than the axial tilt question, but it points to the same underlying reality. The moon is woven into the physical dynamics of this planet in ways that are almost invisible until they're suddenly missing. Now let's talk about something that is going to hit people much more immediately and personally than tidal disruption or axial tilt or day length. Let's talk about the night. Without the moon, the night sky of Earth would be fundamentally transformed. On a clear night away from city lights, when the moon is absent, the Milky Way is already strikingly visible. But the moon spends roughly half of every night above the horizon, and during full moon periods it bathes the landscape in enough light to cast shadows. Remove the moon permanently, and every night becomes a dark night. As dark as the darkest moonless nights we currently experience, but every single night. The stars would be more vivid. The Milky Way would be a permanent fixture of the night sky, visible to everyone, every clear night, everywhere on Earth. This sounds romantic, and in some ways it would be beautiful. But consider what it means for every creature that depends on moonlight. Sea turtles navigate to nesting beaches using the moon's reflection on the water. Remove the moon and their navigation is disrupted. Coral reefs spawn in synchronized mass events triggered by the full moon's light. The largest sexual reproduction event on Earth happens when thousands of coral colonies release their eggs and sperm simultaneously in response to the lunar cycle. Without the full moon, the synchronization signal disappears and coral reproduction collapses. Dozens of species of fish, insects, and birds use moonlight for navigation, feeding, and reproduction. The ecological consequences of permanent darkness would ripple through food webs in ways we are only beginning to understand. Dung beetles, remarkable creatures, navigate by the Milky Way when the moon is absent. They are the only known insects to use galactic navigation. But most nocturnal animals depend primarily on moonlight. Remove the moon and the nocturnal world, which represents roughly 30% of all vertebrate species on Earth, is plunged into deeper darkness. Predator-prey dynamics change. Hunting patterns change. Species that relied on moonlight to find mates or food face new selective pressures. Evolution would eventually adapt, but evolution takes thousands of generations, and in the immediate aftermath of the moon's disappearance, the ecological disruption would be significant. And there is something else about the moon's disappearance that would affect human civilization almost immediately. The calendar. The oldest calendars in human history were lunar calendars. The Islamic calendar is still purely lunar. The Hebrew calendar is lunisolar. The Chinese calendar, the Hindu calendar, the Ethiopian calendar, all of them are built around the moon's 29.5-day cycle. The word month comes from moon. The word Monday comes from moon's day. Menstrual cycles are named after the moon, from the Latin mensa, meaning month. Remove the moon and you remove the original template for timekeeping that nearly every culture on Earth developed independently. The practical disruption would be enormous for the billions of people whose religious observances, Ramadan, Rosh Hashanah, Diwali, Easter, and dozens of others, are calculated based on the lunar calendar. The cultural and religious shockwave would compound the physical and ecological crisis. Let's also address something that scientists discuss seriously, even though it sounds like science fiction. The moon may have played a crucial role in the origin of life itself. One leading hypothesis about how life began involves tidal pools, shallow coastal pools that filled with seawater at high tide and then partially evaporated as the tide receded, concentrating organic molecules. In the early Earth, the moon was much closer than it is today, perhaps 3 times closer, and tidal forces were dramatically stronger. The tidal pools of early Earth would have filled and emptied dozens of times per day, providing a natural chemistry laboratory where organic molecules could concentrate, react, combine, and potentially generate the first self-replicating molecules that eventually became life. Without the moon, those tidal pools might never have been dynamic enough to kickstart the chemistry of life. We might not be here at all. The moon may not just be a feature of the Earth system. It may be the reason the Earth system ever produced life in the first place. Now let's talk about something even more extraordinary and even less discussed. The moon has protected Earth from bombardment. Not directly. The moon is not a shield in the way some popular accounts suggest. But the moon's gravitational presence has subtly influenced the trajectories of objects in the inner solar system over billions of years. More concretely, the moon itself has absorbed an enormous number of asteroid and comet impacts over its history. Look at the moon's surface. It is cratered almost beyond comprehension. Every one of those craters represents an impact that hit the moon instead of the Earth. Some of those impactors were large enough that, had they hit Earth instead, they could have caused mass extinctions. The moon has taken hits for us. It has served as a partial gravitational buffer, and its battered, cratered face is the record of that service. Without the moon, some of those impacts would have hit Earth instead. Not all of them. The geometry is complex, and most would have missed Earth regardless. But statistically, over billions of years, the presence of a large moon in Earth orbit has modified the impact rate on Earth. Remove the moon, and, over geological time, Earth would likely experience a somewhat higher rate of large impacts. Combined with the eventual axial instability, the long-term prospects for complex life on a moonless Earth are considerably grimmer than on the Earth we know. Let's come back to the human story. Because in the immediate aftermath of the moon's disappearance, beyond the ecological and physical consequences, there would be a profound and civilization-shaking psychological and social crisis. Human beings have used the moon to navigate for tens of thousands of years. Ancient seafarers used the moon to sail at night, to estimate their position, to predict weather patterns. The moon's phases were used by farmers across the ancient world to time planting and harvesting. The moon appears in the oldest cave paintings. It is woven into the mythology, the religion, the art, the literature, and the psychology of every culture that has ever existed on Earth. There is even serious scientific debate about whether the moon influenced the evolution of human consciousness itself. The argument goes roughly like this. The predictable 29.5-day cycle of the moon provided early humans with a reliable, visible natural clock. The ability to track the moon's phases and predict events, the next full moon, the next new moon, the next spring tide, may have driven the development of abstract thinking, numerical reasoning, and long-term planning in early Homo sapiens. Some researchers argue that the lunar calendar was the first genuinely abstract intellectual achievement of the human species, the first time our ancestors tracked something that repeated predictably but wasn't immediately visible or tangible. If this hypothesis has any truth to it, then the moon didn't just create the conditions for life. It may have shaped the kind of minds that eventually built telescopes to study it. Remove the moon, and you remove something that has been encoded in human culture, human biology, and possibly human cognition since the species began. The psychological trauma would be unlike anything we have ever experienced. Not just the fear of what physical changes were coming, but a profound grief, a loss. The moon is the most familiar object in the human sky. Every child who has ever pointed at it and said moon is participating in a gesture that goes back to the very first humans who looked up and gave it a name. And now it's gone. The sky where it used to be is just empty. And that emptiness would feel, to millions of people, like something fundamental had been ripped out of the universe. What would governments do? In the immediate crisis, there would be an attempt to understand what happened. Every space agency on Earth, NASA, ESA, Roscosmos, ISRO, CNSA, would be mobilized. Observations would confirm, within hours, that the moon had simply ceased to exist at its location. There would be no debris trail, no gravitational anomaly in the location it once occupied. It would be as if it had never been there, which would be even more terrifying than if it had exploded, because an explosion, at least, makes physical sense. A simple disappearance does not. The scientific community would be in a state of absolute unprecedented crisis, because the disappearance of a body of that mass, in that way, is not compatible with any known law of physics. It would imply something about the nature of reality that our entire scientific framework has no room for. In the weeks that followed, the tidal disruption would be settling into a new, moon-free normal. The tides would become weak and solar-driven only. Coastal ecosystems would be in chaos. The fishing industry, which feeds billions of people globally, would be severely disrupted because fish spawn and feed according to tidal rhythms. Aquaculture operations globally would be recalibrating. Weather patterns, which are subtly influenced by the moon's tidal effect on the atmosphere. Yes, the moon produces atmospheric tides as well as oceanic ones, would shift in ways that climate models would struggle to predict without lunar forcing data. The global agricultural system would face enormous uncertainty. Here is something remarkable that most people don't know. The moon has a tidal effect not just on the oceans, but on the solid rock of the Earth itself. Earth tides, they are called. The solid ground beneath your feet is being flexed by the moon's gravity, lifted by as much as 55 centimeters at the sublunar point, and this solid Earth tide propagates around the planet as it rotates. Remove the moon, and the solid Earth tides cease. The rock of the Earth relaxes. This might sound trivial, but some geologists believe that solid Earth tides may influence volcanic and seismic activity by subtly modulating the stresses on tectonic plates and magma chambers. Whether losing the moon would change earthquake or volcanic activity in the short term is genuinely uncertain. The science is not settled, but the possibility cannot be dismissed. In a world already reeling from ecological and social upheaval, a potential shift in seismic patterns would add yet another layer of uncertainty and fear. Let's think about what humans would do next after the immediate crisis. Because human beings are extraordinarily adaptive, we have survived ice ages, supervolcanic eruptions, pandemics, world wars, and mass extinctions that wiped out the majority of species on Earth. We are, arguably, the most resilient large-brained species that has ever lived on this planet. And in a world without the moon, we would adapt. The tides would become weak and predictable in their solar rhythm. Coastal ecosystems would eventually reach new equilibria, though with significantly reduced biodiversity in the intertidal zone. Agriculture would adjust to the changed conditions. Religion and culture would mourn the moon and then, over generations, incorporate its absence into new mythologies and new calendars. The night sky would become something new and beautiful. Without the moon bleaching out the sky, the stars and Milky Way would be visible to everyone, every night, all over the planet, including in moderately light-polluted suburban areas that currently never see the Milky Way. Astronomy would undergo a renaissance. The permanent darkness of every night would give radio telescopes, optical telescopes, and amateur stargazers a quality of sky that currently only exists in the most remote dark sky reserves. In this one sense, the loss of the moon would enrich our relationship with the rest of the universe. But the long-term future of a moonless Earth would be deeply uncertain. The gradual destabilization of Earth's axial tilt, unfolding over millions of years, would eventually produce climate swings that modern civilization would not survive. When the tilt reaches extreme values, the tropics would expand and contract wildly. The polar regions would experience temperature extremes that currently have no parallel, ocean circulation patterns would be disrupted in fundamental ways, and the stability of the global climate system that has supported complex life for hundreds of millions of years would be gone. Life would not disappear entirely. Life is extraordinarily resilient, as proven by its survival through the asteroid impact that killed the dinosaurs, through multiple ice ages, through the Great Dying that wiped out 96% of all species 252 million years ago. But the specific form of complex, technological, civilization-building life that has emerged on Earth over the last few 100,000 years, that life would face existential challenges within a geological eye blink. There is something almost unbearably poignant about all of this. We take the moon for granted. Every single night, it rises and crosses our sky, pulling the oceans, steadying our axis, darkening some nights and illuminating others, and asking nothing of us in return. We write poems about it. We fall in love under it. We use it as a metaphor for distance and beauty and longing. But we almost never think about what it's actually doing for us. We almost never think about the fact that it is the reason our seasons are what they are, the reason our coastlines are what they are, the reason our nights are what they are, possibly the reason our species evolved the capacity for abstract thought, and quite possibly the reason life emerged on this planet in the first place. The moon is not a decoration. It is infrastructure. It is the most important piece of infrastructure in the entire Earth system. And it is a piece of infrastructure we have done absolutely nothing to maintain, protect, or even appreciate in any scientific sense. Now there is a real-world dimension to this thought experiment that deserves serious attention. The moon is not going to vanish overnight. Physics doesn't work that way, and the disappearance we've been imagining is in the realm of science fiction. But the moon is, in a very real sense, leaving us. Slowly. The tidal interaction that has been slowing Earth's rotation is also pushing the moon outward. It recedes from Earth at a rate of about 3.8 centimeters per year. In the long future, if Earth and the moon both survive the sun's eventual expansion into a red giant, the moon would slowly spiral outward until it reaches a distance where the tidal forces are in equilibrium. After that, Earth's rotation would have slowed so much that a day would be as long as a month, with Earth and moon locked in mutual tidal synchrony, always showing the same faces to each other. It would be a profoundly different planet, cold, slow-rotating, with barely any tidal energy. Not a catastrophe by human timescales, but a geological transformation of the Earth system. There is also a more immediate human concern about the moon that is worth discussing. Right now, in the 21st century, the moon is becoming contested territory for the first time since the Apollo era. Multiple nations, the United States, China, Russia, India, Japan, South Korea, the UAE, have active or planned lunar missions. The south pole of the moon, where water ice is believed to exist in permanently shadowed craters, is particularly coveted. Water ice on the moon can be split into hydrogen and oxygen, rocket fuel, and breathable air. A permanent human presence on the moon, using lunar water, could become a staging post for the rest of the solar system. The moon that we never thought about is suddenly enormously strategically important. We are in the early stages of a new space race, and the moon is the first prize. Understanding what the moon means to Earth, understanding all of this, is no longer just an academic exercise. It is directly relevant to decisions being made right now by governments and space agencies about our future relationship with that familiar, underappreciated neighbor in our sky. So what is the moon ultimately? It is a world. It is a shield. It is a clock. It is a tide engine. It is an axial anchor. It is possibly a cradle for life's chemistry. It is certainly a shaper of human consciousness and culture. It is the largest object in Earth's sky, the one most familiar to every human eye, and the one whose influence on this planet runs deeper and is more consequential than almost anyone fully appreciates. And it is going away. Not tomorrow, not in our lifetimes, or the lifetimes of any humans we can imagine, but slowly, steadily, measurably, 3.8 centimeters per year, the moon is receding. The tides are weakening, imperceptibly slowly. The nights are getting, infinitesimally, a little darker each millennium. And the planet that formed alongside the moon, that has been shaped by the moon for 4.5 billion years, is very gradually, on the longest of timescales, learning to be alone. We are extraordinarily lucky to be alive at this moment in cosmic time. Lucky to live on a planet with oceans, with seasons, with the specific axial tilt that produces our particular pattern of climate and weather. Lucky to have nights illuminated by that silver light that has been a companion to every human who has ever lived. Lucky to have a sky that contains, moving slowly among the stars, the one object that more than any other has defined what it means to live on this earth. Look up tonight. If the moon is there, look at it. Really look at it. Not as a light in the sky, but as a world that is doing something for you right now, silently, invisibly, without any acknowledgement or gratitude. It is holding your seasons steady. It is pulling your oceans. It is making the night beautiful. And it has been doing all of this since before the first creature on Earth ever had eyes to see it. Don't take it for granted. The universe, it turns out, is not obligated to give any planet a moon like ours. Most planets don't have one. Most worlds spin in the dark without any companion, without any tidal anchor, without any stabilizing presence in their sky. We got lucky. Extraordinarily, improbably, magnificently lucky. And that luck, the luck of the moon, is written into every cell of your body, every season of your year, every tide on every beach you have ever walked. It is the oldest and most intimate luck in the history of life on Earth. And if it were gone tomorrow, we would only then understand, finally and completely, what we had always had.